We will take a few examples, I mean two examples which are important. Okay, so first one, find the CTFT of a periodic rectangular wave which we have seen before. Okay, so find the CTFT of the following signal. Okay, and what is that signal? It's a periodic rectangular wave which we have already seen. So minus t1 to plus t1, and again this would be t minus t1, this is t plus t1, and in negative time also we have a rectangle. So this is minus t minus t1, this is minus t plus t1, and this repeats. Okay, for this signal we already have the Fourier coefficient. So for this signal ak is, okay, so you remember here, for this signal exponential Fourier coefficients, for this signal ak would be equal to 2 sine k omega naught t1 divided by k pi. We already proved this result. You can refer Fourier series notes. Okay, yes, so this implies the Fourier series representation. Fourier series representation is Fourier series representation of x of t is, how do you write here? For the given signal, x of t is equal to summation k equal to minus infinity to infinity. We should have ak, but ak is how much? You have 2 sine k omega naught t1 divided by k pi. Okay, and this flow is multiplied with e power jk omega naught t. So this is the Fourier series representation. So we can find the Fourier transform as what? So just now we have seen. So this should be this, the Fourier transform of x of j omega would be, everything remains same except that we have to find the Fourier transform of e power jk omega naught. So this should be summation k equal to minus infinity to infinity. You will get 2 sine k omega naught t1 divided by k pi multiplied with, and this flow will have 2 pi times delta of omega minus k omega naught. So I think I have made a small mistake, and what is that? So Fourier coefficient, there is no 2. ak is equal to sine k omega naught t1 by k pi. So this 2 will not be there. So here also we don't have 2. Okay, sorry for that. Yes, so final Fourier transform would look like this. So but what will happen, this pi will get cancelled out, and we can write this finally to be summation k equal to minus infinity to infinity. I write 2 sine, because 2 is there, this 2 will come here. So 2 sine k omega naught t1 by k, and this fellow is multiplied with delta of omega minus k omega naught. So that would be the Fourier transform of periodic rectangular wave. Okay, so we'll take second example which is important, which is find CTFT of delta t of t. You remember what is this? Yes, it is a periodic impulse train. Okay, so find the Fourier transform of periodic impulse train. Okay, so but before we go into that, we already know what is the Fourier, because a periodic impulse train, this fellow's Fourier coefficients we already know. What is that? So I'll plot that first. So delta t of t is what? It's a periodic impulse train, right? So this is periodic impulse train. So minus t, 0, t, and so on. So this is our delta t of t, with each Dirac delta with strength how much? 1. Okay, so that is the plot of delta t of t. But we know that this fellow will have what as Fourier coefficients, are exponential Fourier coefficients. We got that to be how much? ak equal to 1 by 2. So this implies the exponential Fourier series representation of delta t of t, exponential Fourier series representation of delta t of t is how much? So we write delta t of t is equal to summation k equal to minus infinity to infinity. Ak is 1 by t multiplied with e power jk omega naught t. Okay, this is exponential Fourier series representation. So this implies this is our x of t, correct? So this fellow's Fourier transform would be how much? X of j omega would be equal to same rule, summation k equal to minus infinity to infinity, 1 by t is a constant, and this fellow will have what as Fourier transform? 2 pi delta of omega minus k omega naught. Okay, so that would be the Fourier transform of periodic impulse train. So if you try to plot that, so this is also periodic impulse train. So if you look at this 2 pi by t, we will keep it out. So you get what? Summation k equal to minus infinity to infinity delta of omega minus k omega naught. So what is this again? This is also periodic impulse train in which domain? Frequency domain with period how much? Omega naught. Okay, so note that x of j omega is also periodic impulse train. Okay, is also periodic impulse train in frequency domain. Okay, periodic impulse train in frequency domain. Okay, in frequency domain with period how much? With period omega naught, correct? With period in frequency domain. Okay, with period omega naught. Okay, so what is time domain signal? Time domain signal is also periodic impulse train, and frequency domain signal is also periodic impulse train. So this is very special type of signal. So what is that? The signal will have itself as the Fourier transform. Okay, that is nice. We'll write down that. So what is that we have got? So we have got a period. We'll plot in time domain again. Okay, so this is the summary of what we have got. So we have a periodic impulse train in time domain with period t, and the strength of each Dirac delta is how much? 1. And this follows Fourier transform, how much we got? It is also periodic impulse train, okay, with omega. So, and where are the Dirac delta functions located? At minus omega naught, 0 omega naught, and so on. And but what is strength of Dirac delta here? It is 2 pi by t. Okay, so note that omega naught is also 2 pi by t. So what did we get? The Fourier transform of periodic impulse train is also periodic impulse train. So this implies what? Periodic impulse train, correct? So impulse train will have itself as the Fourier transform. Okay, so it will have itself as CTFT. Means what? Periodic impulse train will have periodic impulse train as the Fourier transform. Okay, so this is very special signal. So there are many signals which will have themselves as the Fourier transform. So if you are interested, you can go through them. We will see one of them, which is a Gaussian function. When we solve problems in the end chapter problems, then we will try to find out the other signal, which is Gaussian signal, which will have itself as the Fourier transform. But the periodic impulse train will have itself as the Fourier transform is very important for us, and we will use this when we talk about sampling theorem. Okay.